Hello everyone, welcome to this sixth lecture in the course on solar photovoltaic system design. So today we will be looking at solar radiation in little more detail, and we will understand what are the different types of radiation data sets which are available and how to use those data sets to estimate the solar radiation resource available for a solar PV plant. Because if we want to set up a solar PV plant, we should understand that solar radiation is the fuel for the PV plant. So, higher the solar radiation available at a location, more will be the output or electricity generation from a solar PV plant. So, before we decide that whether we want to set up utility scale solar PV plant at a location or not, the first step should always be to estimate the solar radiation resource available at that location. Only when we find that there is a sizable radiation available, which will lead to a very healthy electricity generation from the solar PV plant at that location, then we go ahead with the decision to invest into a large scale utility scale solar PV plant. So, going ahead, let us try to understand it from the fundamental concepts. So, in the last class we talked about the components of radiation, the DNI, DHI and GHI. Now, as we understand, weather is a fluctuating phenomena. It keeps on fluctuating from day to day. So, as I speak today, just to give you an example, till yesterday we had very good sunshine here in Roorkee, but today morning suddenly the weather has changed. It is completely cloudy and it is rainy. So, there is a drastic change. Since last 4 or 5 days we were having very good sunshine and very high radiation which was available, but suddenly today we see that it is cloudy and it is completely rainy type weather. So, how do we characterize the weather at a location? That is a major question. If I want to analyze that at a given location, what would be the typical weather profile, then how do we go about characterizing it? That is the question we want to answer. So, for doing that, there is one special type of radiation data set which is used, that is known as the typical meteorological year or TMY. So, this TMY data set is what is used for quantifying the or characterizing the weather at a particular location. So, because as we understand, year to year the weather pattern would be different. So, this particular concept of TMY helps us sort of characterize or give a characteristic weather profile for a given location. And as the name indicates, it is the typical meteorological year or the typical profile of weather at a given location. So, for this particular concept, let us understand how to create this TMY data set or the typical meteorological year data set. So, the first step is that we do meteorological measurement of some of the important parameters for at hourly intervals for a long duration. So, typically for this we would like to measure the irradiation at the location, we would like to measure the temperature, wind speed and wind direction, relative humidity, precipitation, atmospheric pressure. So, all these different parameters we would like to measure, and these are already, every country has a particular meteorological department. In India we call it as IMD or the India Meteorological Department, which does that measurements. So, we are already capturing these parameters. Now, how do we use these to find out the TMY? Now, the typical meteorological year can be formed from different perspectives. So, we can have the typical meteorological year from the radiation perspective, from temperature perspective, from wind speed perspective, or from the precipitation perspective. From different perspectives we can form the year, but because in this course we are talking about solar PV and our interest is to estimate the solar radiation available at a location, so we will frame our TMY from the irradiation perspective. That is our prime concern. We want to characterize what is the radiation profile at a given location. So, to start with, as we said, we will do the measurements over a long period of time. So, suppose for example, it can be at least 20, 25, 30 years. So, suppose I make these measurements, let us say starting from 1991, then 1992, 1993, different years, and go on till 2020. So, I have 30 years of radiation data set. Now, as you understand, each year there are 12 months. So, you have January, February, March, so on till December, and same way for each year we have those 12 months. So, I am just putting those values here because we will be using this to explain the concept. So, like that we have 12 months across these 30 years where we are capturing the data. And what now we are doing is that for this entire duration, this entire 30-year duration, we are capturing the hourly values of all these meteorological parameters, right. So, we are taking hourly values of radiation, of temperature, wind speed, and so on, all these different weather parameters. Now, what we do once we have this huge data set, 30 years data set on an hourly time resolution for all these different meteorological parameters. So, what we do is that we go one by one, we decide the typical meteorological month one at a time. So, we first choose what is the typical January, what does the typical January look like at that location, what does the typical February look like at that location, and like that we go month by month. So, what we do is that for each month the average radiation over the whole measurement period is determined. So, let us say if I start with January, I will take all these January radiation values and find the average solar radiation over this entire period. So, the number of values in that data set would be, you have 24 hours in a day and then 31 days in the month of January, and multiplied by whatever n number of years you are taking, considering for your database. In this case, for this example, we are considering n equal to 30 years, but that is not a rule. It is just suggested that it should be a sufficiently long period over which we are collecting the data, so as to characterize all the types of weather variations at that particular location. So, we can at least 20 is what is recommended, 20, 25, 30 years data would be suitable. So, in this case we will have this 24 into 31 into n number of values for radiation, and then we average it out. So, we take the average solar radiation, I average I will say here, and averaged for month of January and from period 1991 to 2020. So, I will find out this average radiation over the whole measurement period. Now, what I want to do is that basically I want to see which of these 30 Januaries is coming closest to the overall average across the entire 30-year period. So, what I will do next is that I will find out the average radiation for each January. So, for January of 1991, I will average out the values of radiation. So, 24 hours multiplied by 31 days. So, those values I will average, I will get the I average for January of 1991. Same way I will do the averaging for the year 1992 January. So, again 24 cross 31 values, I will get the average irradiation for the month of January for 1992. And like that I will continue doing that same thing for each year till I finally land up with this I average January 2020. So, I have these 30 monthly average values. So, now what I will do is that I will compare one at a time each of these values with the overall average. So, I will compare what is the difference between 1991 January average versus the January average for the entire 30-year period. Then I will compare 1992 average January radiation with the average radiation over the entire 30-year period, and same way I will keep doing for each year for the entire 30-year period. And then the particular January month which has its value closest to the overall average radiation for the month of January for the 30 years, that particular January month I will choose as the representative or the typical meteorological year month. So, I will construct my TMY year, and let us say for suppose for example I found that January of 1996, that year the average radiation comes out to be closest to the entire 30-year average. So, I will put here the January of 1996 in my TMY data set. Same way I will repeat for each month. February, again I will do the same process, take the average radiation for each February in the 30-year period, and whichever average is coming closest to the overall 30-year average radiation for February month, that month goes into the TMY dataset. Suppose for example February of 2007 comes out to be closest in that entire 30-year period, and like that I'll construct the TMY data, and suppose for December I got whatever 2016 or something, anything. I mean, it's not in a sequence per se. I mean, somehow the value I just chose put here as a random example. Suppose for August you got 1992 as the typical month representing the typical irradiation profile. So like that. So each, as you can see in the TMY dataset, each month might be coming from a different calendar year. But the criteria is that particular calendar month represents the most typical value of radiation at that location for a long duration. So whichever month's radiation is matching closest to the 30-year average, that particular month I am picking and putting in my TMY dataset. And when I am saying I am putting that in the TMY dataset, what it means is that I will take all the parameter values, 24 cross 31 values of January, I will pick from that year all the values as it is and put in the dataset. For February, I will pick all the 24 cross 28 hourly values for all these parameters, not just radiation, but radiation, temperature, wind speed, relative humidity, precipitation, atmospheric pressure, dew point temperature, whatever are the characteristic variables representing the weather of that location. All those variables for all the hours in that month I will put in my TMY dataset, and like that here also 24 cross 31 values like that. So finally I will have a dataset with all the hours, 8760 hours, 365 days cross 24 hours. And now the way I have designed this, these particular 8760 values, they are characteristic of the weather of that location. They represent the typical weather of that particular location. Okay. So that is the concept of typical meteorological year. Now question might arise in your mind that why are we doing all this, all this effort, or so to say all this circus, why are we doing it? Anyways, we are averaging it. So why don't we just take the average value of radiation for that particular January and just put it in the TMY dataset? That can be a simpler solution. Someone might say like that, that I just, let's say I take the hourly average. So I take the average value of radiation in this 30-year period, 8 to 9 am. What is the average radiation? I find out the average for the entire 30-year period. I find the average for 9 to 10 am, like that. So I can just take hourly averages for the entire 30-year period and put that average value in the typical meteorological year. That question might arise in someone's mind. We can just do a simple exercise. Why to do this, all this complication, taking the average of each month, taking the average over the entire period, comparing each month average with the entire period, then whichever is coming closest, we are putting that actual value in TMY dataset. Why all this circus? So to answer that question, I would like to show you this particular figure, which would probably explain that concept in a better way. So this is the reason. So if you see here, if we just simply average the radiation, for example, we can do the averaging for any variable for that matter. So here we are talking about the irradiation, and if you just simply average out the radiation, you will get the blue curves like that. Basically what will happen is that you will kill out all the variations, all the fluctuations. It will be just a uniform sort of curve across the entire duration for the entire month. But as we understand, weather does not behave like that. It does not go in smooth curves throughout. Rather, as we understand, there are a lot of fluctuations in the weather parameters. From day to day, as I mentioned, yesterday in Roorkee we had a sunny day, today it is a cloudy day. And sometimes on the same day, let's say morning the sun is out, but by afternoon clouds are there, rains are there. And sometimes within a span of few minutes also. So that is why those fluctuations are important to capture, because they sort of capture the typical profile of weather at a location. And that is why TMY is important. As you see here in the TMY dataset, the red curve, the fluctuations have been captured. Some days are having very low radiation, some are having very high radiation, some days are having somewhere in between. Then there are a lot of fluctuations on some days it is just a smooth profile. So all those different types of variations which are typical of the weather profile of a location, those are captured through the TMY dataset. If we were to take just the simple average, then all these fluctuations would die out, and that would be a artificial thing, which that's not how weather behaves, and that's not how your solar PV plant would behave. So that's the reason why we go with the TMY data set. Now, having understood that, let us look at a typical TMY file format. So, as we mentioned, the measurements are made on an hourly basis, and then you have the overall values across the entire year, 8760 hours. So, this is what the template of the file would look like. You will have the year mentioned. So, the TMY data set here mentioned. Sometimes if you are just talking about the GHI radiation, you can't call it as the TGY. If you are sometimes someone is just talking about the DNI radiation, they might call it as a TDY, but those are like specific special cases. But in general we call it as the TMY, where we have all the weather parameters, not just the radiation but the entire gamut of variables, meteorological variables. So, like this example here, they have taken the data collection period from 1998 to 2016, and they found 2016 year to be representative month in that case. Somewhere another example, 1998 to 2017 as the overall period, and the 2017 month as the representative TMY month, like that. So, that is how this nomenclature is. And then you have for each row of that particular file, it will be mentioned what is the month of the year, which day of the month it is, what is the hour number. Minute is usually 0 because we are measuring on an hourly basis. Then these are the typical meteorological parameters which will be captured in the TMY data set. So, you will have dew point temperature, the 3 components of radiation, DHI, DNI and GHI. You will have temperature, pressure, wind direction, wind speed, and also surface albedo, which is nothing but the reflectivity of the ground for irradiation. We will talk about surface albedo in little more detail in a later class, where we talk about the estimation of solar radiation in more detail. So, these are some of the typical variables which will be there in the TMY data set. Now, let us see how to make use of this TMY data set for our purpose. Our purpose here is to find out the output of a solar PV plant. So, if I want to estimate the solar PV power generation, how much would be the electricity generation from a particular solar PV plant. As we mentioned, the fuel for the solar PV plant is the solar radiation. So, for this we need to get the solar radiation at that location. Solar radiation is the fuel. Depending upon solar radiation being high or low, the solar PV power generation would be higher or lower. Now, this solar radiation, as we discussed earlier in the previous classes, that there are 3 components in which we talk: DNI, DHI and GHI. We talked about these 3 components earlier. So, the question arises that which of these 3 components should we consider? Should we just take DNI or DHI or GHI, or some combination of all these 3? So, to understand this particular question, how to answer this question, we should look again, revisit these 3 components, and if you see, actually none of these would satisfy. Why is that so? Because if you see DHI and GHI, they are defined for a horizontal surface. So, GHI and DHI, they are defined for a horizontal surface. How much is the global radiation or total radiation and the diffused radiation falling on a horizontal surface. Whereas DNI, as we talked about in the last class, we use a pyrheliometer for measuring the DNI, and that is measured on a plane perpendicular to the direction of the radiation from the sun. And this plane obviously has to track the sun. So, when the sun is vertically overhead, then this plane would be flat. When sun is at a particular direction, it will be perpendicular to that particular direction. So, that plane is tracking the sun throughout the day on which we are measuring the DNI. But as we understand, today most of the solar PV installations, they are fixed tilt systems. They are not tracking systems. Rather, currently the standard for solar PV systems is usually the fixed tilt systems. Why is that so? We will come to that later when we talk about the plant design in more detail. But as of now, we will just look at this, that usually, as is a common observation, you might have observed that most of solar PV systems currently are fixed tilt systems. They are not tracking. So, DNI also will not do the job, right. So, DNI, DHI and GHI, none of them on their own can tell you the exact solar radiation falling on the solar PV panel. So, for that, what we use is what we call as the POA, or plane of array radiation. Array refers here to solar PV array. So, how much is the irradiation in the plane of array? That is what we want to find out actually. So, if I have put my solar PV panel at some particular tilt angle beta, let us say, then there is some diffused radiation coming on this particular panel, there is some beam radiation coming. The beam radiation also angle will keep changing as the sun moves in the sky for the observer. So, I need to estimate what is the plane of array radiation, how much radiation is falling on the plane of my PV array. To do that, there are different types of models which have been developed. These family of models are what are known as the transposition models. So, these transposition models, they take as input your DNI and DHI values. Also, I mean GHI can be there, but as we mentioned, if you have two of these three data sets, DNI, DHI and GHI, out of these three, if you have any two, the third can be found out. So, let us say if you just take DNI and DHI as the input to the transposition models, and then there are a few other inputs, the about the location of the place, what is the particular time. So, some locational parameters, some time related parameters, what is the time of the day, which day of the year is it, and like those different variables which characterize that particular location. Then the transposition models are designed in such a way that they give you the plane of array radiation. Now, this plane of array radiation, it is composed usually of three components. One is the beam radiation, which is coming due to the DNI component, the solar radiation coming directly as a beam and hitting the solar PV panel. Then there is a diffused component due to the diffused radiation in the sky, and then there is a reflected component or the ground reflected component coming due to reflection from the ground. So, just to illustrate this, we can represent these three components with this diagram. So, as you can see, this is a pitched solar generator, that means a solar PV panel having a tilt angle beta in this case, and there are these three components. So, the direct radiation is what gives rise to the beam component of the radiation. Diffused radiation is already shown here, and then there is some ground reflected radiation also which hits the solar PV panel. So, we want to estimate all these three, B, D and R, let us say in short we call them. So, B plus D plus R will be equal to the plane of array radiation. Now, there are, as we said, these are transposition models. So, the transposition models help us understand what is the plane of array radiation, to estimate that, quantify that. Now, these transposition models also are broadly categorized into two categories. One is what is the known as isotropic models, and another category is what is known as the anisotropic models. They differ mainly in terms of how the diffused radiation is being quantified. Beam radiation is very clear, it is similar across all the models. Reflected is also not much of a concern. It is mainly about the diffused radiation. How do we estimate the diffused radiation? So, the isotropic, as the name indicates, iso means same, tropic means direction. So, these family of models, isotropic models, they assume that the diffused radiation is coming equally from the entire sky, which is sort of an okay assumption, but not really very accurate. Because if you just commonly on any given day, on any sunny day when the sun is out there in the sky, if you just go out and look at the sky, what you will see is that obviously sun is the brightest part in the entire sky, but also interestingly the portion of sky which is around the sun, that portion is sort of more brightly lit. So, let us say if you are looking at the sky in the morning hours 9 AM, 10 AM, sun is still in the eastern half of the sky. So, the eastern part of the sky will be little more brightly lit, whereas the western part of the sky will be little not so bright, and vice versa. If you look at it in the sky in the afternoon on a sunny day, suppose 3 PM, 4 PM, the sun has moved to the western half of the sky, and you will see the western half of the sky is little more brightly lit as compared to the eastern half of the sky, which is a common observation. So, in reality, the diffused radiation is not coming equally from all directions of the sky. Wherever the sun is located, that portion is usually more brightly lit. So, these anisotropic models, they take care of that particular anomaly or sort of the difference in the diffused radiation coming from different portions of the sky. So, they differ in terms of how the diffused radiation is estimated. So, diffused radiation estimation is little more detailed in the anisotropic models. However, then the complexity of the model also increases. In this course, we will look at one simple isotropic model because these are more simpler there is a slight error but not much, depending upon the location, how many clear sky days are there and how many cloudy days are there. There might be some error, but usually you can say 5 to 7% is hardly the error between isotropic and anisotropic models. But isotropic models are remarkably simpler. So in this course, we will be talking about one isotropic model. We'll be looking at the equations and also estimating the values of radiation for an isotropic model in more detail. And that isotropic model, the most popular one, is known as the Liu-Jordan model, which was sort of formulated and validated way back in 1960. This was published as a research paper, and over the years people have found that this is a very fairly simple and fairly accurate model. It gives a very good trade-off between simplicity and accuracy. So we will look at this Liu-Jordan model in a little more detail, and we'll see how isotropic models can be used for estimation of the plane of array radiation. So let's quickly move ahead to the model. Before we end today's class, we'll at least have an overview of the beam component, and then we'll move ahead in the next class for the other components. So in this Liu-Jordan model, this is how we measure the beam component. Now this equation might seem a little daunting. It's quite having a lot of terms here. If you see, a lot of trigonometric terms are there, different sines and cosines of different angles are there, and then multiplication of different sine cosine terms, and then 5 such terms are being added. So might seem a little daunting, but we'll break it down for you in the next class in more detail. But for now, we will look at just an overview of this particular equation. If you see, there are these 5 independent variables or inputs which are going here. Delta is the declination angle, phi is the latitude of the location, which is quite easy to comprehend. Whatever is the latitude where you are located, that is the phi angle. Like in Roorkee, we are around 28-29 degree latitude. So that is the phi for this location. If you are located at the equator, phi will be 0 degree. If you are located at Tropic of Cancer, then your phi will be 23.5 degree, and accordingly. But if you go in the southern hemisphere, the sign convention is that we measure the latitude, we call it as positive in the northern hemisphere and negative in the southern hemisphere. So if you are at the Tropic of Capricorn, we will call it as minus 23.5 degree. So like that, latitude is pretty well understood. Beta is the module tilt. We just now saw that you have a tilted module. We usually have tilted PV module. So whatever is the tilt angle, that is the beta. Then R angle will come to in short while. So declination angle and R angle we will be looking at in the next class. For now, we will look at this psi, which is the module azimuth. Module azimuth basically represents what is the direction or orientation of the panel, in which direction the panel is facing. And as it says here, it is the orientation of the panel measured from south to west. So let us look at the psi or the module azimuth in a little more detail. So this is usually the sign convention we follow for module azimuth. So you have 4 directions: south, north, west and east. So usually we call the south direction as the 0 degree, that is the reference direction. Then we go in a clockwise direction. So south is 0 degree, then west is 90 degree, north is 180 degree and east is minus 90 degree or 270 degree. So we follow this sign convention for module azimuth. And also, as it says here, typically for a fixed azimuth system or a system which is not tracking the direction of the sun or the orientation. So for a fixed azimuth system, if we are in the northern hemisphere, then we put the panel facing southwards. So therefore, the default azimuth angle is 0 degree for the northern hemisphere, and vice versa. If we are in the southern hemisphere, we put the panel facing north direction, or 180 degree azimuth is the default in the southern hemisphere. So basically, the panel should always be facing the equator. If you are in the northern hemisphere, 0 degree is the default. If you are in the southern hemisphere, 180 degree is the default. So that is the module azimuth. Now, as we mentioned here, if you put psi equal to 0 degree, which is the standard for northern hemisphere, let us say we talk about a person in the northern hemisphere. So we have psi equal to 0 degree, and interestingly, the other 2 variables which we talked about, beta and phi, they also have a correlation. So usually, I mean, this has been fairly well understood and studied, that if I want to optimize my PV panel output, the PV electricity generation around the year, if I want to maximize it, then the most optimal tilt angle beta is same as the phi or the latitude of the particular location. So, these are the two standard design parameters for PV plants, that we put beta equal to phi, the tilt angle same as the latitude of the location, and psi equal to 0 degree for an observer in the northern hemisphere. So, with respect to an observer in the northern hemisphere, let us try to simplify this complicated equation using these two assumptions. If you have beta equal to phi and psi equal to 0 degree, what would this equation boil down to? Give it a try on your own. Use your pen and paper and try to solve it out. Usually I give that as a simple classroom exercise to my students in the class, and you will see it is very interesting. If you use these two assumptions, this very daunting and scary looking equation will boil down to a very small equation. Give it a try on your own, and you will see if you put these things here. So, sin psi, as we know, sin 0 degree is 0. So, this term becomes 0, this entire term is gone. What else happens here? Cos psi is 1. So, this particular component will be gone, it will be 1. Here this you have cos psi again here, this will be gone, this will be 1. And in the remaining thing, now you use this other thing beta equal to phi. So, if you see here, this is sin delta and you have sin phi cos phi, that is the first term. Second term is minus sin delta cos phi sin phi. So, as you can see, these two also cancel out. So, these first two terms are also gone. And for the third and fourth term, if you see, this also is a very interesting one. So, you see you have cos delta cos phi and another cos phi, because we are taking beta equal to phi, multiplied by cos HRA plus cos delta sin phi, another sin phi, and cos HRA. And here simply if you take out cos delta and cos HRA as the common terms, you will get cos square phi plus sin square phi, which we all know is the most popular trigonometric identity. Cos square phi plus sin square phi equal to 1, and therefore, your B is nothing but dni into cos delta cos HRA, and you see the beauty of the equation. So, if we take the most idealizing assumptions, which always any PV plant if you set up, you will get the maximum output with beta equal to phi and psi equal to 0 degree for the northern hemisphere, and you will see you will get B equal to dni cos delta cos HRA, which is a very simple equation. And now this delta and HRA, declination angle and R angle, as we now see, they have a very major role to play. So, we will be talking about them in more detail in the next class, and I will give you a homework exercise. Just try it out, try this same simplification for the southern hemisphere. And for the southern hemisphere, again we will assume beta equal to phi, that is same, but psi equal to 180 degree, right. And if you look at it in little more detail, as we just now said, if you take the sign convention into account, we said that latitudes in the southern hemisphere, they are negative, but your tilt angle can never be negative. You cannot put the panel beneath the ground. So, tilt angle will always be positive. So, if you take the sign convention into account, then actually this will become beta equal to minus phi. So, for southern hemisphere, you have beta equal to minus phi and psi equal to 180 degree. So, this I am giving to you as an exercise. Try it on your own. Put beta equal to minus phi and psi equal to 180 degree in this scary looking equation, and see for yourself what does B become, what does the beam radiation boil down to. So, with that we will stop today's lecture, and in the next lecture we will look at the solution to that particular question which I have given you, and also we will look at the other two components, the diffused and the reflected component, in the Liu Jordan model. Thank you.